Assalamualaikum and good day to everyone. Today we're going to continue with chapter 6 phase equilibrium. These are the content for chapter 6. At the end of this chapter, the student phase. Phase is the homogeneous part of the system, a distinct homogeneous part that is in contact with other parts but separated from them by a distinguishable or well-defined boundaries. A system can exist in solid, liquid or gas phase, or furthermore can coexist in any combination of two phases or even three phases at once. For example, gas or a gaseous mixture, it is a single phase. Miscible liquid, it is a single phase. Example, water and ethanol. Because water and ethanol can mix very well, so it will form single phase. Mixture of immiscible liquid, it is two-phase. Immiscible liquid is an element with two electrons and a mixture of two different states of substance. Substance that can coexist in three different states, solid, liquid, and gas, able to form a three-phase system. As you can see in this diagram, there are ice cube and water. So ice cube is a solid phase and water is a liquid phase. So this one is a two-phase system. One-phase system. There are no boundary between the substances. For example, gas-gas system. Mixture of gas, macam air, okay, oxygen and nitrogen. So you won't see any boundary between the substances. So it forms one-phase system. Another example, miscible liquid. Mixture of water and ethanol. Both of water and ethanol can mix very well, so it able to form one-phase system. Two-phase system. Two substances with a boundaries separating them. For example, mixture of water and oil. Both of them cannot mix very well, so it forms two-phase system. Another example is ice cube and water, so it forms two-phase system. Three-phase system. Three substances with boundaries separating each other. For example, ice, water, and water vapor system. Component C. Component is a chemically independent constituent of a system. The number of components, the minimum number of independent species required to describe the composition all of phases present in the system, or the number of substances present in the system. Example, ice and water. Ice is H2O, water is H2O. So only one component present in the system. Mixture of water and ethanol. So they are H2O and ethanol. So two different substances. So it is two components. Water and CCl4. There are two different substances present in the system. So it is two component system. This table shows the number of phase and component. As you can see here, air, the mixture of gas, oxygen, carbon dioxide, and nitrogen. So there are many of substances present in the air. So the number of components is many. And then the phase is gas, and then the number of phases will be 1. Another example will be ice and vapor. Ice cube is solid, vapor is gas. So there are two different phases. Since that ice and vapor is H2O, so the number of components is only 1. Iodine crystal and iodine vapor. So iodine crystal is solid, iodine vapor is gas. So there are two number of phases. However, both of them are iodine, so only one substance present in the system, so only one component present in the system. Phase changes. The diagram shows the nomenclature for the different phase changes, most commonly used to describe transition between solid, liquid, and gaseous state. For example, freezing process. It is the phase changes where a liquid turns into a solid when we lower the temperature below its freezing point. Another example will be sublimation. It is the phase changes where a solid turns into a gaseous without go through a liquid phase. The phase diagram. It shows the region of pressure and temperature at which its various phases are thermodynamically stable. Shows the equilibrium pressure-temperature relationship among different phases of a pure substance in a closed system. Phase diagram can be used to predict changes in the boiling and melting point by the changes of temperature and pressure. So you're able to predict the physical state at specific temperature and pressure. Phase boundary. A boundary between regions shows the value of pressure and temperature at which two phases coexist in equilibrium. This is the phase diagram in general. This one is pressure. This one is temperature in degrees Celsius. There are three main features of a phase diagram. The first one is area or region between the line that correspond to the stable phase, solid, liquid, and vapor of a component. Solid phase is stable at low temperature and high pressure. Liquid is stable at intermediate temperature and pressure. Vapor is stable at high temperature and low pressure. The second one is line that correspond to the temperature and pressure under which two phases are in equilibrium. For example, solid and liquid. This one solid liquid equilibrium. And this line corresponds to the liquid vapor equilibrium. And then this line corresponds to the solid vapor in equilibrium. And the third one is triple point O, temperature and pressure at which all three phases of a substance coexist in equilibrium. So that means solid, liquid, and vapor berada dalam keadaan equilibrium at this point. The phase diagram. The equilibrium can exist not only between the liquid and vapor phase of a substance, but also between the solid and liquid and the solid and gas phases of a substance. So this one, solid to liquid, it is a melting process. Liquid to solid, freezing process. Liquid to gas is vaporization, and then gas to liquid is condensation process. And then solid to gas, sublimation, and gas to solid is deposition process. Line AD is the solid and liquid phase are in equilibrium. Line AB, liquid and gas in equilibrium. This line AC, solid and gas in equilibrium. Example 1. The phase diagram for a substance A is shown. State the physical state of A at the condition of X, Y, and Z. Solution. At condition X, compound A exists as solid and liquid in equilibrium because dia terletak pada line. So solid and liquid in equilibrium. At condition Y, dia berada pada line. So liquid A and gas A exists in equilibrium. And at condition Z, dia berada pada region ataupun area. So the substances A exists as a solid only. Gibbs phase rule. The phase rule. A general relation among the degree of freedom F the number of components C, and the number of phases P at equilibrium for a system of any composition. So formula dia adalah degree of freedom equal to component minus number of phases plus 2. Degree of freedom or variance F, the number of intensive variable that can be changed independently without changing the number of phases in equilibrium. The intensive variables could be temperature, pressure, or concentration on the phase equilibrium as well as chemical constituent equilibrium. So this formula is Gibbs phase rule. This formula only applies to system in chemical equilibrium. And the number of two is two intensive parameters, normally temperature and pressure. The phase rule, general rule. If you have equilibrium balance between reactant and product, the number of components will be reduced by 1. If you have equal amount or concentration of product form, the number of components will also be reduced by 1. So maknanya C2 akan reduce by 1 if you have equilibrium balance between reactant and product, ataupun if you have equal amount of concentration of product form. Example 1. Solid sodium chloride dissolved in water. So available chemical constituents are 4. Na plus ion, Cl minus, NaCl, and H2O. However, Na plus and Cl minus have the same amount. Equal neutrality has sodium chloride. Then component of C is equal to 2 and not 4. The phase rule, example 2. This equation shows the calcium carbonate solid decomposed to the calcium oxide solid and carbon dioxide gas. So available chemical constituents are 3. Is it correct to say C equal to 3? Because of the equilibrium condition, the number of independent components is reduced by 1. Thus, C equal to 2 instead of 3. Can you specify the number of phases for the reaction? We have here 3 homogeneous, distinct parts of the system separated by definite boundary. Thus, P equal to 3. The phase rule for water system. How many components do you have? So only one component, which is H2O. In the one-phase region, one can vary either the temperature or the pressure or both within limit without crossing a phase line. So this region will have degree of freedom equal to C minus P plus 2. So C component, only one component H2O, minus the number of phases, since that dia berada pada region ini, so the number of phases will be 1. So 1 minus 1 plus 2. So it equal to 2 degree of freedom. So along a phase line, we have two phases in equilibrium. For example, this one, liquid and vapor in equilibrium. So the number of phases will be 2. If we want to stay on a phase line, we can't change the temperature and pressure independently. So along a phase line, the degree of freedom will be 1 number of components minus the number of phases 2 plus 2. So it will be equal to 1 degree of freedom. This one is triple point of water system. So at the triple point, there are 3 phases in equilibrium, solid, liquid, and vapor. But there is only one point on the diagram where we can have 3 phases in equilibrium with each other. So at the triple point, the degree of freedom will be equal to component, the number of components will be 1, H2O. The number of phases, solid, liquid, and gas, 3. So 1 minus 3 plus 2, so the degree of freedom will be 0.